So I wanted to look at other ways and more systematic ways to build chemical functionality into how LLMs work. And the problems are the poor understanding of the smiles, the poor math skills, and the lack of knowledge in specific areas. So I wanted to see if it'd be possible to overcome this. And the techniques that I utilized here are RAG and MIPRO, which I'll describe. And the property that I used as just a demonstration is topological polar surface area. So TPSA is a concept that originated from Peter Ertl paper in 2000. And this is a straightforward concept that's proved to be very powerful. And the idea is that you can do a simple calculation just from a chemical structure without a three-dimensional structure and get a numerical value for what the polar surface area of that molecule would be. And then it's possible to do this with a simple group contribution method, where you would take a table like the one from the Ertl paper, find the functional groups by these wildcard matches, and then sum up the polar surface area contributions for all the functional groups within the molecule to get a TPSA value. So retrieval augmented generation is a technique being widely used in LLMs and most commonly for text augmentation. So many companies that are building chatbots are, for example, using this as a method to augment the LLM's responses with additional documents that are available to the LLM that are, for example, conversant in the operations or the products of that company. So what the previous example that I showed you of using the assistant where it was able to use a chemical Python package, RD kit, in order to gain chemical accuracy, really inspired me to think about how we could use direct code to do operations like math and chemistry and to augment the generation of the LLM. And then the other tool comes out of the Stanford Natural Language Processing Lab called MIPRO, or Multi-Prompt Instruction Proposal Optimizer. And this, as they advertise, is an effort to substitute prompt engineering with programming. So to get the benefits of creating these very nuanced prompts that have been shown to improve the results from LLMs, but to do this in an automated fashion using PyTorch to evaluate and select the parameters. So this is done in a process where you generate many different bootstrapped example sets, candidate instruction sets, and then evaluate how well these work against a metric. So the metric in this case is the mean absolute error and the prediction of the TPSA value. So the model that I selected here is GPT-4o mini, and that's not a frontier model insofar as it's a smaller version of 4o, estimated to be about 7 billion parameters. But that was an intentional selection because that's a safer way to avoid too much knowledge within the training set, and gives room for growth. So the idea here is that it would be possible to improve upon the base functioning of the LLM. And in this case, the base functioning of the LLM is poor. So when given a set of smiles codes for molecules, the root mean squared error is 46.74 for making predictions. And the majority of these are well over the actual calculated TPSA value, and none of them really fall on the accurate prediction line. So the technique that I'll break down how this works in a second using RAG and MIPRO did a good job in most cases of improving those predictions and getting onto a perfect prediction, although there remain outliers. So this is reducing the amount of hallucination, but not eliminating it. So the root mean square error is 7.44 in that case. In this case, the direct prompt without these additional flourishes is just asking the LM to predict the topological polar surface area given a Smiles code. So the modified prompt is more complicated, has many parts, and then each of these parts we subsequently removed in an ablation study to see which of these were having the most impact. The base query, part A, is similar to the direct call to the LLM, just asking for a TPSA from a Smiles code. The retrieval augmented generation parts add some calculated answers using tools like RDKit. So one of the things this provides is a list of the functional groups that are present in the molecule. That's part B. Part D is just a count of the number of nitrogen, oxygen containing atoms that might have these functional groups. And then part E is the values from that ERDL paper for the TPSA values. And then there's other things added in here to coerce the LLM into providing the response in the format that's desired. So knowing that the LLMs aren't particularly good at math, we want to get numerical answers as a list and then do the sum of those independently just using Python rather than risking that the LLM might be accurate in everything else and then fail due to the addition problem. So with all of those pieces in place, again, the RMSE value is 7.44, so a good improvement over the direct call to the LLM. And then replacing the group descriptions, there's a modest loss in performance with the RMSE dropping to 8.51. If the data table from the ERDL paper is eliminated, so those specific values aren't provided, there's still quite a few predictions on that prediction line, suggesting that the LLM may have some of that information in its training data, but the performance drops to 10.81. Removal of all of the RAG elements drops the performance to 28.95, generally underestimating as opposed to the overestimate of the direct call, and some of the values coming back at 0. The MIPRO portion is independent from those RAG elements, and this is the result of what occurs during the optimization. So bootstrapped examples are created and signatures or decorators around these prompts are added. Different ones are tested, evaluated, and selected. So examples are shown there, sometimes straightforward, sometimes a little more coercive, like telling the LM that this is a high stakes pharmaceutical modeling decision. So dropping those signatures actually doesn't have a significant impact. So although MIPRO does improve the performance, the major improvement is not from the decorators of these flourishes and text added to the LLM prompts, but more comes from the bootstrapped examples. So losing those drops the performance of the model more substantially, even though some still do perform well. So the goal here is not to build a TPSA predictor. There are many, and you can calculate them directly or obtain them from PubChem. So the goal here really is to demonstrate a method of improving how LLMs handle chemical information. And again, it's not specific to any one model. This, by a few changes in the underlying code, can be moved to any other LLM. So this is all stuff done without having to retrain an original model, without having to fine tune a model, or build your own LLM that is conversant in your particular area of interest. So that makes this a little more universal, portable, and adaptable. So I think overall, this points, among other things, to the fact that LLMs can handle chemical information given the right tools, and that some of these tools could really make improvements in how LLMs handle chemistry. I'll point out that a lot of generative AI labs spend billions of dollars on training and evaluating models, and the entirety of all the data in those slides cost about 40 cents So generative AI research doesn't have to cost billions.